Can we do it? I mean, I believe in my heart you guys can do it. The question is whether I can do it. I don't know. At the moment. Let's see here. He says, since fn of x is less than or equal to f of x, almost every x, we have the integral of fn is less than or equal to the integral of f for all n. Is that by lemma? Is that by Fatau's lemma? Or is that just... I think that's just the monotonicity of the integral, right? At the moment. And hence, the limit supremum as n goes to infinity of the integral of fn is less than or equal to f. Makes sense, right? Yeah. But then what do we have? Fatau's lemma says that the integral of f is what? Did I say? I think I'm missing a little something here. Yeah, kind of important. The integral of f is what? It's less than or equal to the lim inf. And what does that give you then? If we have both of these things. I guess I could just write this right here, right? So that this implies that, so therefore this and this must be equal because of how we defined, like this, the limit superior has to be above or equal to the limit inferior. So by that string of inequalities, they must be equal, because inequality would not go well for us in terms of the superior being bigger than the inferior, right? So we have to have equality, and equality then forces f to be equal to both of them. And when these are equal, of course, that means the limit itself exists, and that limit is equal to f, which is corollary 1.8. Okay, great. Now, moving along here. So he says that this inequality, not so I read. He says, in particular, we can now obtain a basic convergence theorem for the class of non-negative measurable functions. Its statement requires the following notation. So, yet more notation. I'll put it over here. So what would we mean by Fn? F. This is meaning what? He says we write this. This means that this sequence of measurable functions such that what? Fn of x is less than or equal to Fn plus 1 of x for almost every x. And of course, n, anything you like. And also the limit as n goes to infinity of Fn of x is equal to f of x, almost every x. So both, this inequality for the functions in the sequence, and also that the limit of the sequence of functions is f, again, both for almost every x. We put those two together and just say Fn goes to f. As in, done? Hooray! Thank you. When will I have this graded? I don't know.
Just like before.
I think.
Will you wait until the others take it? That's my question.
Probably.
That's fine.
Yeah. I think the others are taking it Tuesday, although I don't know about that.
Oh, yeah, they are taking
I don't know about that creature named Liam yet. When's he going to do it? I don't know. The sooner Liam takes it, the sooner I grade it.
Okay.
Although I'll be in Arkansas, so these can kind of be tricky for me to grade them. There's that. But yep. Okay. And so what if instead of this we had Fn wee like that? All that's going to do is put a greater than or equal to here. Yeah. That's what that's going to mean, right? And with that language, we are able to write the monotone convergence theorem. So suppose this is theorem, corollary 1.9 in our current lingo. Corollary 1.9, which is the monotone convergence theorem. So suppose you got a sequence of functions, measurable, non-negative, with Fn going to f. Then the integral of Fn, the limit of that guy, is just equal to the integral of the limit function f. How is this different than what we just did? The difference is that have we dropped any hypotheses from corollary 1.8? I mean, we've obviously added the comparison of n and n plus 1, right? Like the sequence of functions is point-wise almost everywhere decreasing. Yeah, this Fn of x less than or equal to Fn plus 1 of x. Limit, I mean, there was no inequality over here in corollary 1.8, right? We just had non-negative measurable functions. They were all bounded above by the limiting function. Oh, that's the difference here. There's no statement. There's no statement that there's at least no direct statement that f of x is above the sequence, right? Like corollary 1.9 doesn't. We don't have to have this, right? That's missing. Yeah, I think you're right. I'm just saying that like that's the difference in the presentation, right? But I think you're absolutely right. I think that this implies that, but this does not imply that necessarily. Yeah, absolutely. I agree with that. Well, the advantage of corollary 1.9 is you don't need to know what f is. I mean, it gives you a method of calculating this with that when you don't know this, provided that condition's met. Okay, I guess still, well, that's what I think, but I see the tension. Don't let me leave without this. Let me put it over. All right, so corollary 1.10. Maybe the answer to why 1.9 is interesting will become apparent as we look at further results. Look at this. So consider a series. Summation k equals 1 to infinity of a sub k of x, where a sub k of x non-negative, measurable, for k greater than or equal to 1, then this is neat, the integral of the series is equal to the series of the integrals. And he says if the series of the integrals is finite, then the given series converges for almost every x. Probably should prove this to appreciate corollary 1.9, because I'm guessing that the proof here involves corollary 1.9. But I'd almost rather just talk about what this corollary says. What does this say? I mean, obviously it has applications to like power series and Fourier series and all kinds of things, right? Because we're looking at a sum of functions, non-negative, although I guess sums of sines and cosines not exactly non-negative, right? Let's get on with it. I still want to get to the definition. So that's corollary 1.10. Now he uses this to do something really interesting, something called the Borel-Cantelli lemma, or something like that. And he has another illustration here that has specific calculations in it. I'm try to come back to these at the start of next time because I think I need to be totally awake to do these properly. So I'm going to try to come back to the examples. These are really, I think they look intriguing to me. I'm going to try to work these out next time we meet, going from page 63 to 64. But we've now reached stage 4. So let's say it. Let's see here. Okay, over here. And actually, I think stage 4 is the sort of easiest of the various transitions, building up the final full-blown case of Lebesgue integration, stage 4, general case. All right. And so what he does is he says, let f be any real-valued measurable function on Rd. Then we say that f is Lebesgue integrable or just integrable if the non-negative measurable function, so f is Lebesgue integrable if the absolute value of f is integrable in the sense of the previous section. All right. And, okay. In that context, he now explains what that integral actually looks like, all right? So let me break it down. Oh, come on. All right. It's a really neat trick, all right? So he says, let f be Lebesgue integrable. He says f plus of x. You can just let be the max of f of x in 0. And f minus of x would be the minimum, max of minus f of x and 0, right? So both f plus and f minus are what? They're non-negative, right? I mean, see, because, and what else is that you can write f as equal to let's see here, f plus what? So if f of x is 0 or positive, okay, great. But if f of x is negative, then you want to do this. If f of x is negative, then the f plus is 0, and the f minus is minus f of x. So you put a minus to bring it back to f of x again. That's just an identity. And of course, if it's 0, well, these two different silly things agree, right? They just both give you back 0. So we have a decomposition of f into a sum of these, well, a difference of these non-negative functions, right? And but we've already defined how to integrate non-negative functions, right? So going back to linearity and all that for stage 3, we can define the integral of f as this. Well, I'm not defining it, I'm just calculating it, right? The definition happened already in stage 3, really. Well, is this the definition? Goodness, what is the definition technically? I guess we're actually defining the integral of f at the moment, because this was just name calling over here. I said f is Lebesgue integrable, right? But saying it's Lebesgue integrable and not telling you how to calculate the Lebesgue integral isn't really a complete definition, right? It's like I say, Emily's an astronaut, but I never explain how she's going to go to space. You know, we could just start talking about Emily the astronaut, but it wouldn't be reasonable. Do you have any plans? I mean, do you have plans for being an astronaut at some point?
No.
Okay, just checking. You never know. We have worked in a lot of space this semester. Some of them outer spaces too, right? Yeah. Outer space, inner space. What? Super space? Yeah. Not in here, though. I try to behave. Okay, so, but then he says, well, okay, great, but how do you know that this is uniquely defining the integral, right? What if you had a different decomposition? You know, what if you could write, you know, what if f was equal to f1 minus f2, where f1 and f2 were non-negative, and you had a different decomposition of non-negative functions, like that, right? g1, f1, and f2, all of these being non-negative. Suppose you had two different non-negative decompositions of a given Lebesgue integrable function. Then he says, okay, well, if that was the case, then, excuse me, then that would give us that f1 plus g1 equals to f2 plus g2, right? Actually, how do you get that? The thing I see is that f1, I mean, the only thing I see right offhand is that f1 minus f2, oh, well, I got that already. Okay, it's my confusion is based on the wrongness of what I wrote. So this is good. There's still hope for me. All right. Thank you. Where did it go? He says, but both sides of this identity consist of positive measurable functions, so the linearity of the integral in this case yields. So if you know this, then since everything here is non-negative, oh, and was there more here? How does he know it's positive? Positive, how are you going to positive measurable functions? Where do you get positive from? Both sides of this last identity consist of positive measurable functions. I think it's non-negative, yeah. So we can integrate, and we get the integral of f1 plus the integral of g2 equals the integral of f2 plus the integral of g1, right? And then if you subtract, you get back to the two different potential definitions for the Lebesgue integral. So what that says then is that this uniquely defines the Lebesgue integral for a non-negative function. We can just take the difference of the integral of the positive piece and minus the negative piece, so to speak. Right, as so defined there. Oh, he says, in considering the above definitions, though, it's useful to keep in mind the following small observations. Both the integrability of f and the value of its integral are unchanged if we modify f arbitrarily on a set of measure 0. He says it is therefore useful to adopt the convention that in the context of integration we allow our functions to be undefined on sets of measure 0. He says, moreover, by 5, which I've erased, of proposition 1.6, it is finite valued almost everywhere. Thus, availing ourselves of the above convention, we can always add two integrable functions f and g, since the ambiguity of f plus g, due to the extended values of each, resides in a set of measure 0. Moreover, we note that when speaking of a function f, we are in fact speaking about the collection of all functions that are equal to f almost everywhere. So we'll say more about this next time we meet. But and then he says proposition 1.11, the Lebesgue integrable of functions is linear, additive, monotonic, and satisfies the triangle inequality. So the things we had with us at stage 1 are still with us here. And although proving, I guess, well, no, that's fine. But the proposition 1.12 seems very intuitive, but it takes a fair amount of work to prove. And then that brings us to the, as he says, the culmination of our efforts thus far, which we'll talk about next time. But it's theorem 1.13, which says if we have a sequence of measurable functions, then, well, it's essentially the theorem that, it's essentially corollary. It's not exactly corollary 1.8, but it's an awful lot like corollary 1.8 or corollary 1.9 or one of the other theorems I said earlier today, except now for big boy measurable functions such that fn goes to f of x as x goes to, as almost every x as n goes to infinity. What I'm trying to get at here is the theorem is now for Lebesgue integrable functions, not just for non-negative functions, you know. And the theorem basically says that we can pass limits inside the integral for the Lebesgue integral. And then he has a page on how to integrate complex valued functions. And it's stupidly easy. Basically, it just says that if the real and imaginary parts of the complex function are Lebesgue integrable, then the complex function is Lebesgue integrable. And it describes how to calculate it. It's just a simple like a simple add-on to what we've done. Then he talks about the space of L1 integrable functions, and that is a very interesting section that we should look at. And hopefully this leads us to some applications like I think he has some things to say about Fourier series soon after this, and I'm hoping we can get into that by next time. So Fubini is always tempting, but I wonder if I should. That Fubini theorem. Have a good break, guys. I still owe you guys problems.
Yeah, I was going to ask you that.